It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, we might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be?
Welcome, chemistry neighbors. So what should have happened by now is you should have taken a 12.2-4 quiz and then tried to look up the words and things. For verification purposes, I'll just give you a read through. So 1 is condensation, 2 is evaporation, 3 is dynamic equilibrium, 4 is vapor pressure, 5 is boiling point, 6 is endothermic, 7 exothermic, 8 is heat of vaporization, 9 is heat of condensation. So some explanation of what these mean in conjunction with what it would look like in the next form. When you go to read 12.5, that'll be a much smaller read. If you're sort of not liking that read because there was a lot of new points, I don't blame you. But for 12.5, there's 2. For 12.6, there'll be 2. For 12.7, there's 5. You don't have a day quite like that ever again. There's no day in this chapter that'll match the 9 new ones. So you just took your heaviest reading hit for sure. The heaviest new question change around hit would be from today into next, because a heavy reading day leads to a heavy switch around day. But if you can get through the switch arounds today, the chapter dramatically slows pace then. So that's the good news, bad news scenarios on this. When you go to do the next one up, again, the 12.5, there's 4 new points, 12.5. Did I just say 4 a minute ago? I don't feel like I did, but maybe I did, I don't know. But there's 4 new points, 12.5, that's for sure. Then the questions from today's number 10 down, those all just stay the same. And then there's a reworking at the top. So I'll just sort of talk about this, I think, for a minute, and then I'll tell you what the reworking is about. So condensation, notes that I have in my condensation category here is, other than the basic explanation that's been typed, condensation happens more easily if you have low temperature. If you're turning gases into liquids, you don't want it to be hot, you want it to be a little cooler. That's what makes things turn into liquids. Like dew at night deposited in your yard is because it's cooler. Boiling water on your stove is going the other direction because it's hotter. So to make gases to liquids, low temperature is helpful. High pressure is helpful. That process is exothermic. More word on exothermic in a minute when we get a little bit lower. I'll just do that now. Exothermic, skipping down to 7, that's when heat gets released. So if you are putting heat into a liquid like water, you're putting heat into it on your stove to try to boil, that's endothermic. When you go the other direction, that has to be exothermic. There has to be heat being released. 2, evaporation is the opposite scheme. Evaporation happens more easily if there's high temperature or if there's low pressure, and that's endothermic. Evaporation helps you cool. They talked about getting out of a pool on a hot day. You get that chill because that heat is being given off, being absorbed by you. So endothermic is going to cause like a cooling process that evaporation goes with. And they explained that some in the book. Dynamic equilibrium doesn't really have any real important notes on there. It's just the idea that something's going one way and something's going the other way, and it's sort of like in balance. If I'm at the beach and I'm digging out a hole for my kids, getting sand off out of the hole, and meanwhile the kids are behind me shoveling sand back in the hole, neither of us is going anywhere. Like there's something being done and there's something being undone at the same time that are basically in balance. That's the idea of dynamic equilibrium. It might be some water is becoming steam, some steam is becoming water, and there's like a balance to that. Vapor pressure in 4 is basically just a measurement of how much pressure you have when you're in a position like that. Water's becoming vapor, vapor's becoming water, it's in a state of equilibrium because that's equaled out. You could measure the pressure there, and that would be the vapor pressure. Boiling point, we've had other times. Boiling point is just the temperature where those things are equal. Where the vapor pressure of a liquid is equal to the external pressure that's above the surface. That's the boiling point. If you get above the boiling point, the vapor starts to dominate. If you get below the boiling point, the liquid dominates. But if they're in balance, you are at the boiling point there. Boiling point gets lower at high altitude is something that the book talked about, because when you get to high altitude, there's less pressure. And it's easier for those steam, if you're thinking water, for that steam to escape. It's just easier with less pressure. Unfortunately, for the cooking process, it's not boiling that cooks your food, it's the temperature that cooks your food. So if you're here in Pennsylvania and your water boils at 212 and you're trying to cook something in boiling water, it's cooking at a temperature of 212. You go to Denver, where you're a mile high and you have less pressure, the water might boil at like 180. And then the food you're cooking is only cooking at 180. It's going to take you longer to cook food that way. Just like if you turned your oven to 212, it would cook faster than if you turned your oven to 180. If you're in Pennsylvania, the best you can do is get up to 212 Fahrenheit with boiling water. If you're in Denver, the best you can do is somewhat less than that. I'm making up 180, but something in that range, for example. So if your temperature for your boiling water is going to be lower because it's easier to boil, it takes people longer to cook things there. They talked in the book that it takes 10 minutes to cook an egg at sea level, but it might take you 20 minutes at Pikes Peak, which is way up in the mountains. 6 is endothermic, means heat absorbed. We've had that word before. Exothermic is heat released. We've had that word before. Heat of vaporization is going to be a number we're going to need for homework and grab from a table. In your packet, there was a series of 3 tables early on. It's the middle table that we're going to need to grab heat of vaporizations. At least for today. Over the chapter, we'll need some different tables, but today I believe we just need this table here that's in the middle that has these heat of vaporization. The heat of vaporization just measures how much heat it takes to boil something. 9 would be the same number. That's the heat it takes to go the other direction and turn things back into liquids. So if you look at the table, that table 12.1, for example, water is one thing you'll see a good bit in the problems. Water's boiling point is 100 Celsius, which is 212 Fahrenheit in the American world. There's 2 different systems they can use to calculate heat. One is based on calories. So this column here is labeled calories per gram. For every gram of water, it would take 540 calories to boil it. If you go in reverse, for every gram of steam, to create a gram of water, it would take 540 calories getting released to go in the other direction. Joules is another system to measure heat. Joules and kilograms are the 2 main schemes. Joules are friendlier with kilograms, and it's a much bigger number because kilograms are much larger than grams. So for water, if you had a kilogram of water and you want to boil it, it takes a little bit over 2 million joules, 2.26 times 10 to the 6th joules. And if you reverse the process to make a kilogram of water out of steam, there would be over 2 million joules released from that process. Instead of boiling, the heat would have to go in to make it boil. The other direction, the heat comes back to you. So that's how that table's working, but more on that when we do some math in a moment. So in terms of how these things change, let me look at the next questions. So next time you see this, it'll say in a giant 12-point question, we'll make two contrasting columns worth of ideas. It'll say to name two changes of state. So you would do condensation on one hand and evaporation on the other. It'll ask you to do a definition. For condensation, you could just do what's typed on the quiz. It's converting a gas into a liquid, or turning a gas into a liquid, something about gas becoming liquid. Evaporation, I'm a little pickier on, and I'm looking to hit some of the key words here, which would be escape, molecules, surface, and forming vapor, or forming gas, if you'd rather say gas is fine. But we'd be looking to capture those important words in the answer of it's the escape of molecules from the surface of a liquid to form vapor. You've probably watched water boil before. It's not the escaping from the bottom. The escape is all from the top. It's always from the surface that the molecules escape to make a gas. I will ask you to describe two conditions for these to take place. So in condensation's world, it's high pressure, low temperature. For evaporation to happen, it would be low pressure, high temperature. I'll ask you to classify what type of change that is. So for condensation, you'll say exothermic. For evaporation, you'd say endothermic. And then I'll ask you to define what that means. So for exothermic, you'd say heat released. For endothermic, you'd say heat absorbed. So quick recap forward if you don't need the quick recap. Condensation's category would say condensation, gas turning into a liquid, high pressure, low temperature, exothermic, and heat released. For evaporation, you'd say a longer answer, escape of molecules from the surface of a liquid to form vapor. You'd say low pressure, high temperature, endothermic, and heat absorbed. Then there's a new question that I didn't say a minute ago when I was doing the recap up around condensation, but I took this from the reading of when it talked about condensation. I'll ask, real gases act like ideal gases under what circumstance? And you'd say if the kinetic energy overcomes the attractive forces. Gases have a lot of kinetic energy. If they have lots of kinetic energy, they overcome those attractive forces between molecules. We've learned that liquids have some attractive forces between molecules. If gases can get moving so fast that they have a lot of kinetic energy, they can overcome those attractive forces, so they basically are not there. That's more what a real gas acts like, or what an ideal gas acts like, would act like. So that question was, real gases act like ideal ones under what circumstance? It's if their kinetic energy can overcome the attractive forces. Today's number 3 just goes backward. What is dynamic equilibrium? So you would just go from the word rate on. The rate of a forward process equals the rate of a reverse process occurring at the same time. Vapor pressure just goes backward. You just do the words I typed. In a closed container, it's the pressure exerted by a vapor that's in dynamic equilibrium with the liquid state. Boiling point 5 goes backward. It's the temperature where the vapor pressure equals the external pressure. New question that I did talk about with my egg boiling and all that. What makes boiling point lower is if you're at high altitude. I asked if that takes food then longer or shorter to cook, and the answer was longer. If you're cooking at a lower temperature because of an easier boiling situation, it's longer to cook. 8, 9 will go backward, but you could do some ditto marks to clean this up. So heat of vaporization, you'd say quantity of heat required to evaporate 1 gram of a liquid at its boiling point and constant pressure. And then heat of condensation, you'd say the same thing, but switch to the word condense and switch to the word gas. And then I have 2 final questions that are on the board that will just sort of merge our way into the mathy world. 2 units to measure those heats. Back to talking like if they're coming from the table. 2 units to measure those heats are these: calories per gram or joules per kilogram are the 2 units for heat. A couple mathy examples. So I am headed now to page 316 is where I'm going to grab a problem from. Before I start that, just things that are important to know. One of the units we just looked at was calories per gram that we could grab from a table. Okay, if you're doing any problem with calories, calories can only lead you to grams. Grams can lead you to calories. Those guys have to work together. It's possible in the homework you might have a gram question, but you need to use kilograms, because kilograms can lead you to joules, joules can lead you to kilograms. You might have a little bit of side conversions to do. So if you have a gram problem but need kilograms, because you're trying to get to joules and kilograms can get you to joules, you would do something like this, where you take the grams they give you, cancel away the grams to make kilograms, knowing that 1,000 grams make 1 kilogram. So if they give you a gram number and want you to get to joules, you can't do it. You'd have to work from grams to kilograms to get to joules. The reverse can also happen. They might give you a kilogram question where they give you a kilogram count, and if they ask you to get from kilograms to calories, you can't really do it directly. Kilograms can only get to calories if you work through grams. So if they do that in the homework, kilograms would need to cancel to make grams. Again, 1,000 grams makes 1 kilogram. That's just the way that those need to go. So for problem 12.1, they say we have 28 grams of water. Grams can lead us to calories, so I hope they ask us about calories. And they do, so thank you, book, for doing that. It says calculate the heat energy in kilocalories from 28 grams of steam at 100. The 100 doesn't matter. Water can only boil at 100, so that's an unnecessary fact. But we need to take the 28 grams and run a conversion to get ourselves to kilocalories. So how this will work is we need to cancel grams. So we need grams on the bottom, and we'd like to get ourselves from grams to calories. The link from grams to calories is always going to come from the table that we looked at earlier. So we're talking about water, that's the top line. The calorie gram number is that there's 540 calories per gram. The 540 will always go with calories. Gram just uses the number 1. In some problems, we might be done. If all they asked us for is calories, we would be out. But they didn't ask us for calories. They added on an extra step that isn't always there, but they want kilocalories. 1,000 calories make 1 kilocalorie. If you punch that in, this times 540, divide 1,000, your screen should say 15 point, and something that'll round to 1 kilocalories. For the second one, I'm on 12.2, page 317. They start a step farther away. They start with moles of water. So if they start you with moles of water, we can get ourselves from moles to grams. We've been doing that for a long time using the periodic table. They won't usually give you moles, but if they do, we always use 1 for moles. Add up 16 for oxygen, 1 for each hydrogen from the periodic table, and that would be 18 grams in a mole. We're trying in this question to get to joules, and grams can't get you to joules. Grams can only get you to calories. So we need to get from grams to kilograms. To get from grams to kilograms, it's what we just did right here with 1,000 and a 1. We needed to get to kilograms because kilograms can get you to joules. The way that kilograms can get you to joules is, again, using the table. So if I use my table for kilograms and joules, the scientific notation number, 2.26 times 10 to the 6th, always goes with joules. The kilogram number for using the table will always be a 1. You punch that in, and you get 4, 2, and in the third position it'll round to a 7. a 0 to just complete the number, and that would be joules. Homework on this is based off of 13 to 17. Let me know if you have any questions. See you tomorrow.